Hi again. In this video, we're doing Chapter 10. This is the beginning of the long run. Remember, the short run is where we started. That's when inflation and inflationary expectations, or expectations generally, don't necessarily have to equal the actual outcome. And we looked at how we can get fluctuations in the short run under that assumption. We looked at the medium run, when expectations adjust to reality and we return to the natural rate. Now we're moving to the long run, where we're going to look at economic growth. In essence, how the natural rate of output changes over time. And we're going to start in Chapter 10 with just the facts of growth. Essentially, all we're doing here, it's a relatively short chapter, is just setting up the facts we need to explain with a growth model we'll be developing in Chapters 11 and 12. So the first issue is about measuring the standard of living. And just some quick notes on this. How would we compare standards of living across countries? How do we compare the standard of living in a given country? You know, can we compare now to some long time in the past within the U.S.? How do we do that? Mainly within a country, what you want to use is GDP, or even better, GDP per person. It's sort of a measure about how much stuff there is available for each person to consume. Now, one problem with this measurement, and it doesn't really look at the distribution. So you could have the same distribution, or same GDP per person, if one person owned almost everything and everyone else owned almost nothing. That country might have the same GDP and population as another country where income's much, much, much more equally shared, and these kinds of measures don't get at that. But there's ways to measure those sorts of things too, how unequal economies are. The main thing you use there is something called the Gini, though there are better measures than that you'll learn about in some of the other economics courses if you take them. But the main way in which we look at the standard of living within a country is to look at GDP per person and how that's changed over time. When you're comparing across countries, it's a little more complicated because the prices of goods can differ across countries. You know, the price of a car can be different in real terms, in terms of the relative price, than it is in another country. You can have exchange rate differentials as well that can mess things up. So when you compare across countries, when comparing GDP per person across countries, you want to control for two main things. One is the exchange rate, and secondly, prices, differences in prices. Housing, for instance, might have a very different cost depending upon which country you're in. If you don't adjust for those kinds of things, you're going to get the wrong types of answers when you're comparing how well do people live in these two countries. You're trying to assess well-being here in some sense. We're using GDP per person as our measure of that. You need to adjust for these kinds of things. Numbers that do this, numbers that make these adjustments, are called purchasing power parity numbers. The short is PPP numbers. And that stands for purchasing power parity. And there's other things you need to worry about too. For instance, if the standard basket of goods that you consume in one country is very different from the standard basket in another. The CPI is based upon some notion of what the average person consumes. And so when you measure prices within one country, if the market baskets are very different because they consume different kinds of goods, maybe by custom or for some other reason, you're not really comparing apples to apples. You're comparing apples maybe to oranges because they prefer or consume different sorts of things. And so the typical market basket's also an issue you have to worry about. And there's other things as well. But for the most part, within a country, GDP per person's fine, pretty good measure. Again, you get changes in the market basket over time that are difficult to control for. I mean, we didn't have computers in 1920. How do you make a comparison? But GDP per person, at least over shorter time spans, isn't a bad measure. When you're looking over really, really, really long time periods, like you're comparing the 1400s to today, even GDP per person can be a little bit of a misleading measure, but it's probably the best that we have. So typically that's what you use within a country. Across countries, again, you need to adjust for these kinds of things, and purchasing power parity does that. I'm going to leave the details of the purchasing power parity stuff to your international courses if you ever take them, and hopefully you will. But there's more in the book that you can read up on this if it's a subject that really interests you. They give an example of in a box of exactly how to do this for two countries. And they have a two-good example with different prices and different exchange rates. And they show you exactly what the issues are and how to make these comparisons. Some other things, I've used GDP per capita, but what probably matters more is consumption per person. So we can use GDP per person or consumption per person. That could be different. For instance, in China, the investment is a much larger fraction of GDP than it is in the US. So even if they had the same GDP, consumption per capita would be lower because they're putting so much into investment. And so often what we really care about is how much on average each person is consuming. Sometimes we are interested in productivity differences. And in that case, there's two measures that are used. Output is GDP. Output per person, or better, output per hour. People might work different amounts. And so output per person in one country, they could work 8 hours. In another country, they work 12. Well, the output per hour will control for those difference in the average workday. And so output per hour is typically what we're using when we're interested in productivity differences across countries. The final thing I'll note is that, as I said earlier, I guess what we're most interested in is well-being. And probably when you took 202, you probably talked about all the reasons why GDP is not a perfect measure of well-being. It misses non-market activity. It doesn't control for pollution. It counts bads as well as goods and other sorts of things like that. But there's also perhaps a nonlinear relationship between well-being and GDP per capita. So it may be, what we're really interested in is utility or well-being. And, so a final question is, does happiness, well-being, I guess is a better word. I don't know if it really matters. Well-being. Does happiness increase when GDP per capita per person increases? It may be that what happens is that if you were to look at happiness up here, and GDP per person, per capita, here, it may be the relationship flattens out. And so initially you get lots of increase in happiness for an increase in GDP, but after a while increases in GDP, even per capita, even large ones, don't increase well-being very much at all. There's hardly any effect on happiness because people already have most everything that they want, or most of their needs are being met. And so even when we're looking, if what we're really interested in is a happiness, comparisons of GDP per capita probably should take this sort of nonlinearity into account. But anyway, those are just some issues about measurement. What does actual economic growth look like across countries? So I think the book calls this growth in rich countries. Not all of them, but some of them we're going to look at, since 1950. And this table will have 4 columns and 5 rows, 6 rows. So we're going to have one column will be annual growth rate, growth of GDP output per person from 1950 to 2009. So that's the first column. Then we're going to look at 1950. We'll look at 2009. And then we'll look at the ratio of 2009 to 1950. That'll be the last column. And what we're measuring in these last 3 columns is real output per person. So real GDP output per person. And doesn't really matter, but it's based in 2005 dollars. 2005 is the base year. And then I should have made this column narrower, then I wouldn't have run out of room over there. The countries are France, Japan, the UK, the US, and then we'll want to look at the average. Okay, so for France, the growth rate was 2.5% over that entire period. So that's the average growth rate over this period. Japan was higher at 3.9%. The US was at UK was at 2.0%, and the US was at 1.9%. 1.9, that's supposed to be a 9. And the average was 2.6%. If we look at the actual numbers, I wish I would have left a little more room, but this is $7,112, $3,118, $10,400, and $13,183. So these are in 2005 dollars. So in terms of 2005, that was the income in 1950. Pretty low. If you look at 2009, it's gone up a lot. In France, it's 30,821. For Japan, it's 31,958. For the UK, this is all in your book, it's 33,386. In the US was 41,102. The averages here were 8,453. 34,317. And then we look at the ratio of this to this. It's 4.3, 10.2, 3.2, and 3.1. So what that tells you is, I don't know if you realize this, but just in the last 60 years, from 50 to 2009, the standard of living in the US has tripled. It's 3.1 times. You can buy 3.1 times as much stuff per person on average. For Japan, it's 10.2, and so on. France is 4.3. So here's some things to notice. There are 2 main conclusions the book talks about. First of all is how fast, that's what I was just pointing out, income has grown. How much income's grown over that 60 years period, from 7,000 to 30, 3,000 to 31, that's a huge growth rate, 10 to 33, 13 to 41. So that's the first thing to note. So one Lots of growth. High rates of growth. Think of China. Now, the other thing to notice is we start out very unequal, 13 to 3. That's about a four-fold difference, right? Even 7 to 13, that's almost 2 times as much. So the U.S. to other countries, there were vast inequalities in GDP per capita. If you look in 2009, they're much more equal. There's still differences, but the biggest difference is nowhere near 2, let alone 4 like it was from there to there or anything like that. And so there's been convergence in GDP per capita. We start very unequal, but those countries that are the most behind tend to grow the fastest. So if you look at these growth rates, the further behind they were, the faster they grew. That's the China story too. They started out way behind, they're going really fast, and then what happens is as you grow and get bigger and bigger and bigger, your growth rate tends to level off. And over the long run, there seems to be convergence across countries. And so those are 2 of the facts that we'd really want to be able to explain with any growth model. One, so the conclusion from that thing is that one, there's a large increase in output per person, and that's in all countries. Even the US tripled in 60 years. And 2, convergence of output per person across countries. And that extends to many, many more countries than what I showed in the table, what the book shows in the table. It's not true that every country is catching up and seeming to converge, but boy, if you look at a lot of countries, that seems to be true. And so those are 2 things that any growth model would want to explain. Okay. Next, let's do, it's a several page section here, but it's the last thing. It's really about aggregate production functions. So the title in the book is Thinking About Growth. A primer, an introduction. And we're going to use a framework that's due to Solow, Robert Solow. He's the growth guy in the late 1950s and is still used today. It's what he got his Nobel Prize for. And what we want to do is look at something called an aggregate production function, which you've already seen in the past. We used one earlier. This is just a relationship between aggregate inputs, the aggregate amount of labor you have, aggregate amount of capital that you have, and the aggregate amount of output that you get out of them. So you have these inputs, the aggregate amount of steel, all this stuff. We put all those inputs into a production function, and out jumps a whole bunch of GDP. And so earlier in the course, we had a simpler one. We just said that Y was equal to labor. What we want to do now is add capital, K, and we're going to have a more general production function. And so our aggregate production function is going to be of a form you may or may not have seen before, but hopefully you have. Y is some function of capital and labor. So that's the aggregate labor. This is aggregate capital. And this is output, or GDP, or income, as we know. So we feed, and technology is built into the function. Technology is captured, I'll give you an example in a second, by the function F, in this case, is the name of our function. Typical. So technology is captured in the function F. For instance, here's an example of a production function. It's called the Cobb-Douglas production function. So we can say Y equals A k to the alpha, L to the 1 minus alpha, where 0 is less than alpha is less than 1. So these are just coefficients. So this might be a half. Alpha might be a half, half. A is some number. So we could feed it K and L, and it gives us back an aggregate output. So this is going to capture, here's our aggregate inputs, and here's our aggregate output. So this is a production function. A, in this model, this captures technology. When A goes up, if A increases, we get more output for the same inputs, capital and labor. And so that's like technology getting better. We have the same inputs, but we're making better use of them. So as A goes up, that's like technological change. And the next chapter will actually look a lot, about what happens, the next couple of chapters, as A grows over time, as we get better and better technology. Because that's going to be an important part of the growth story. And we'll mostly use this Cobb-Douglas production function when we actually write down a specific form, because it's nice and simple to work with. It has nice properties. Now, there's something called constant returns to scale. If you remember your micro. Do you remember what that means? And we'll often abbreviate that as CRS. So if you see CRS, it means constant returns to scale. It's often, what that means is if you double the inputs, you double the output. Exactly. And we often assume that aggregate economies have constant returns to scale, because we're talking about economic growth. And as you grow, what you can do is just duplicate. You build another 7-Eleven, another insurance agency, another grocery store, another McDonald's, another Burger King, blah, 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 another Penny's, an award. Well, no, I guess Montgomery Wards is no more. But anyway, you can just build the same sorts of things that you had already. And so there's no reason why, if you're just duplicating existing technology, if you double the amount of your inputs, you're just going to double the amount of your output. And so constant returns to scale is usually assumed. Decreasing returns to scale means if we double inputs, we less than double output. And increasing returns to scale means if we double the inputs, we more than double the output. But we're mostly going to stick with constant returns to scale. So what it means is if you have constant returns to scale, then if I double, say I have y, leave some space here, equals f, leave a space in front of k, and a space in front of n. Am I using n or l? Oh, we've been using n. Sorry, I got l right here. It's n. What this means is that if I double the inputs, so my inputs are k and n, I get y. If I double this to 2 and double this 2, so I double both of those, then I'm going to double y. If this number were 1.5, double inputs, less than double output, that's decreasing returns to scale. If this were like 2.5 or 3 or 4, then doubling the inputs would more than double output, and that would be increasing returns to scale. But again, for aggregate economies, we generally assume constant returns to scale, and that's what it means. More generally, for any number x, what it says is that xy has to be xk plus xn. If we scale x and n and k up by the factor x, output will go up by the factor x. X could be 2, 3, a half, whatever. This relationship would hold. And so that's what we mean in general about constant returns to scale. However, if only one factor increases, we have decreasing returns to scale. So I have y is f of k and n. If I keep this fixed and I increase n, if I double this, I'll less than double output. That's called decreasing returns to scale. We'll draw a picture of that in a little while. And so you only have so many tractors out there. You know, I got 10 tractors and 10 people. If I increase the number of tractors to 11 and increase the number of people to 11, output will go up proportionately. If I go from 10 to 20, both tractors and people, output will be doubled because I've doubled both of my inputs. However, suppose I start with 10 tractors and I only double labor. I take the labor up to 20. Well, 10 people don't have anything to drive. They can go out there with hose or something else or dig with their hands, but they're not going to, output's not going to double. You've got clear decreasing returns to scale in that case. Or you can think of the opposite. Keep the number of people at 10, double the tractors to 20. You know, maybe they can use some when others would have been in maintenance and things like that, so output goes up some, but it's not going to double because you can't drive 2 tractors at once. And so output's going to less than double. And so increasing an individual factor gives you decreasing returns to scale, decreasing returns to capital, decreasing returns to labor. Increasing both proportionately gives you constant returns to scale. Now, if you have constant returns to scale, we can do something that'll be very helpful, and we're going to do this continuously. If you start with y equals f of k and n, remember that x I multiplied before? Let that little x be 1 over n. Remember that xy is f of xk and xn if we have constant returns to scale. If I double both of these, I double this. Well, what this means is I can say that y over n is some function of k over n and 1. That's just a constant. So essentially, this is just a function of k over n. So I can write output. This is output per person. That's what I'm interested in. And this is capital, with a K, nah, capital per person. So what this tells us is something important. It says that output per person, so let me write the 2 conclusions. What could make, this tells us something important. For output per person to go up, y over n, that is output per person, to increase, we need one of 2 things. One, we need capital per person to go up, capital per person, per capita, to increase, or we need technology to get better. That's the F function. If you were to draw this graphically, let me show you what these 2 things are. So let me erase this. I need a little more room. If I were to draw a picture of y over n equals f of k over n and 1, but we don't need to keep track of the 1. If I put k over n, capital per person on that axis, and output per person on this axis, it's shaped like this. This is f of k over n. And what this shape shows us is diminishing marginal productivity. If this goes up by, say, the amount of the black part of the pen, if I increase k over n by this amount, so there's k over n 0, K over N, 1. Then output per person goes up by that amount. But if I start way out here where the curve is a lot flatter and do the same thing, and it's flatter because of the decreasing returns to capital, the way to make this go up is to have K go up with N fixed. And if only K is going up, then you have decreasing returns. Or you can have N going up, going in this direction, and you'd get the same thing. But it's easier to think about with capital. If I increase by exactly the same amount here, I get a much smaller increase in output per person. So it went up that much there, it only goes up that much here. And so as we increase K over N, capital per person, machinery and that sort of stuff per person, factories and all that, eventually it flattens out. So this alone can't be the source of long-run growth. Because eventually you get to this flat part and you don't get much growth in output per person out of any further increases in capital. It becomes too costly. The other way you can get output per person to go up is by a change in technology. And that looks like this. So here's K over N again, Y over N. Here's our initial f function, f0 of K over N. And let's just look at this level of K over N. For those inputs, we get that amount of output. If technology goes up, if technology improves, what that means is for the same inputs, we get even more output. So what technology does is it rotates this curve upward. So when technology improves, this curve rotates upward, and we get even more output per person out of the same amount of input. And this can go on forever. We can keep getting this bigger and bigger and bigger and bigger and bigger. And so there's two sources of growth in output per person. One is for K over N to go up. So the two sources of growth are one, K over N goes up. But that's limited because eventually you hit decreasing returns to scale. The second way is for technology to go up, and that can go on for forever. And so technology is really the key to economic growth. That's what we're trying to show here. And we'll come back to those ideas in the next couple of chapters. But again, there's two ways that you can grow Y over N. One is to move out on an existing production function. It could be on this one, it doesn't matter. That'll cause Y over N to go up. You'll get growth in the standard of living. Or you can have an improvement in technology. And the improvement in technology is probably a much more sustainable way to have economic growth because you don't hit the limits of decreasing returns. Let me just play around with the Cobb-Douglas a little bit, do a little bit of algebra, and show you some of these ideas. So the Cobb-Douglas in general is y is a k to the alpha, l to the beta. But when alpha plus beta equals 1, then we have constant returns to scale. What that means is beta equals 1 minus alpha. So y equals a k to the alpha, l to the 1 minus alpha has constant returns to scale. And I'm going to show you that next. Okay? If alpha plus beta is greater than 1 up there, then you have increasing returns to scale. If alpha plus beta is less than 1, you have decreasing returns. And again, we want it to equal exactly 1 so that we have constant returns because we think that's a good model of the aggregate economy. So we're going to start with that production function with constant returns to scale. Y equals A k to the alpha L to the 1 minus alpha. Now let's prove that it has constant returns to scale. So I'm going to double the inputs. So I'm going to take A, 2k to the alpha, 2L to the 1 minus alpha. And I need to show that equals 2y. I can rewrite this as A times k to the alpha, L to the 1 minus alpha, times 2 to the alpha, 2 to the 1 minus alpha. Oops, I have to put the parenthesis there. Let me write them the same. 2 to the alpha times 2 to the 1 minus alpha. Now, do you remember from algebra, like bases add exponents? Like bases add the exponents. Alpha and 1 minus alpha is 1. This is 2 to the 1, or 2. So this is equal to A k to the alpha, L to the 1 minus alpha, times 2. But what's this? That's just y. So this equals 2y. So I double the inputs, I double the outputs. If this were a beta, you'd get alpha plus beta. If it was less than 1, you'd get less than 2. If it was greater than 1, you'd get greater than 2. And that's how you get greater. This is basically 2 to the alpha plus beta. It equals 1 for us, so we get constant returns. If alpha plus beta was bigger than 1, you'd get increasing returns. If it was less than 1, you'd get decreasing returns. But anyway, the Cobb-Douglas with those characteristics has constant returns to scale. Because it has constant, oh shoot, L equals N. I slip and use L for labor. The book uses N. If you want to, in your notes, erase all the L's and put N's, go ahead. Works exactly the same. Apologies for that. Okay, because it has constant returns to scale, I ought to be able to divide through by n. So let's take and divide by n. So this means that y over L, y over n, I've been using y over n. This is still output per person. L is the number of people. N's better for that. L is labor, but it's measured in numbers of people. I should be using n here. Is equal to, let me do it this way, A times k to the alpha, L to the 1 minus alpha over L. Now, if you remember what this is equal to, I can bring this up to the top, and it's L to the minus 1. I then add the bases. 1 minus alpha minus 1 is minus alpha. So this means that y over L is A k to the alpha, L to the minus alpha. If I bring that up to the top, the 1's go away. Or those have the same exponent. Y over L is A times k over L to the alpha, just like we said. So this is output per person, depends upon, this captures technology. As A grows over time, as we get smarter and smarter about how we do stuff, we get more out of our capital and labor, and Y over L goes up. That's going to be the source of long-run growth. And this is K over L is just output, or capital per person. This has diminishing returns. So again, it looks like this, just like we saw before. This would be A, K over L to the alpha, where this is K over L, and this is Y over L. And then if A goes up, this thing would rotate upward for an increase in A. That's technology. Moving this way is what happens when capital, that's called capital accumulation. So when K over L goes up, when there's capital accumulation, we get growth but it levels off as we grow more and more through that means. One last thing for this chapter, and we're all done. It took a little longer than I thought. Let me show that there's decreasing returns to k. So we can rewrite this as y over L is a times k over L to the alpha. And let's let k go up with L fixed and show there's decreasing returns. And it's actually easier to work with this one. So what I want to look at is dy dk holding L constant. So that's going to be equal to a k to the alpha minus 1. A alpha k to the alpha minus 1 L to the 1 minus alpha. Just we'll differentiate with respect to k, so bring the alpha in front, it's k, to the 1 lower power times this. So that's what you get. So that equals A alpha times L over k to the 1 minus alpha. And what that shows, so what we've shown here is that the change in y, dy, due to a change in capital, is A alpha L over k to the 1 minus alpha. I just rewrote this in case it's off the screen up there. So what does that show? Don't worry, that's too high. Let me do it again. So dy dk is A alpha times L over k to the 1 minus alpha. Make sure that's right. Yes. So what this shows is as k goes up with L fixed, dy dk goes down. So as we keep increasing capital, this number gets smaller and smaller. So the change in output that we get is smaller and smaller. So every increase in capital, as capital gets larger and larger and larger, the change in output gets smaller and smaller and smaller. And that's exactly what we mean by decreasing returns to scale. We're not going to be using this kind of stuff a lot in the next chapter. What you need to know is that we're going to use these production functions. We're going to use a production function of the general form y over n, going back to the n's, is f of k over n. And it has decreasing returns to either k or n. I could have done the last thing with n just the same, and I would have gotten exactly the same answer. There's decreasing returns to n as well. This is y over n, k over n. The production function looks like this, f of k over n. And there's two ways for y over n to grow. We can accumulate capital, and again, that's limited because this eventually flattens out and you won't get any more growth or very little growth if you just rely solely on capital accumulation. Or you can have technological change, which will give you, for the same input, here we're increasing, there's more capital accumulation. Here, for the same k over n, you get a larger y over n. And that's the other way that you can grow. So there's constant returns to scale. That's why we can write it this way. But there's decrease in returns to individual factors. And technology has this effect on the model. So that's the end of chapter 10. And I will see you soon for chapter 11.